All right, welcome back. So what we're going to go over is a little data transformation and feature engineering. And that's going to be a little more specific into EMR. But before we get started, hit the like button, subscribe, and share this with anyone you know who's taking the AWS Machine Learning Associate exam. So why does data transformation matter in AI and machine learning? Before data enters a machine learning model, it must often be cleaned, transformed, engineered. These operations significantly impact the success of a model, especially in high dimensional data, where irrelevant or redundant features can degrade performance. And this is a phenomenon known as the curse of dimensionality. And this is where we come into play with Amazon EMR. This is processing data at scale. So what is EMR? Elastic MapReduce. Okay. So Elastic MapReduce represents AWS's managed implementation of the Apache Hadoop ecosystem. It's designed to process vast amounts of data at scale using distributed computing frameworks. Despite its name referencing the now obsolete MapReduce paradigm, EMR has evolved into a comprehensive platform supporting modern big data technologies, including Apache Spark, Apache Hive, Apache HBase, Presto, Apache Flink, and other framework essential for machine learning data prep and feature engineering. For AI and machine learning applications, EMR serves as a critical infrastructure component that enables data scientists and engineers to pre-process, transform, and prepare massive data sets that would be impossible to handle on single machines. The service provides the computational power necessary for feature engineering at scale, exploratory data analysis on petabyte scale datasets, and distributed machine learning model training using frameworks like Spark MLib. The relevance of EMR to machine learning extends beyond simple data processing. Modern machine learning workflows often require complex data transformations, feature engineering pipelines, and exploratory analysis that must be performed on datasets too large for traditional single machine approaches. EMR provides the distributed computing infrastructure necessary to make these operations feasible and cost-effective, while integrating seamlessly with other AWS services used throughout the machine learning lifecycle. So let's go into EMR a little bit more. Okay, clusters. All right, cluster components. So you have a couple of pieces. The master nodes. These are also called the leader node. These serve as the coordination hub for the entire cluster, managing the distribution of data and tasks across worker nodes while monitoring cluster health and job status. Each and every EMR cluster requires exactly one master node, and it's possible to create single cluster nodes or single node clusters consisting only of a master node for lightweight processing tasks that don't require distributed computation. The master node runs critical services, including the Hadoop Resource Manager, name node for HDFS metadata management, and various application masters for frameworks like Spark and Hive. This node also hosts the web interfaces for monitoring cluster performance and job execution, making it the primary access point for cluster management and troubleshooting. Core nodes. These function as the primary worker nodes that both execute and process tasks and store data in the Hadoop Distributed File System, HDFS. These nodes run essential services, including Data Node for HDFS storage and Node Manager for resource management, making them critical for both computation and data persistence within the cluster. Core nodes provide the persistent storage layer for the cluster through HDFS, which automatically replicates data across multiple nodes to ensure fault tolerance. This replication means that losing a core node can impact data availability, making proper planning and monitoring essential for production workloads. Task nodes serve as optional computational resources that execute processing tasks without storing data in HDFS. This separation of concerns makes task nodes ideal candidates for Amazon EC2 Spot instances, as they can be added or removed from the cluster without affecting data persistence or cluster availability and stability. So the ephemeral nature of task nodes enables dynamic scaling strategies where additional computational capacity can be provisioned during peak processing periods and released when no longer needed. And it provides a significant cost optimization opportunity for variable workloads. So remember these three things. The master, this manages job distribution, cluster health, and job tracking. Core, this is for processing tasks and stores data for HDFS. And task, this runs tasks but doesn't store data. It's ideal for temporary spot-based compute. All right. And cluster deployment patterns. So Transient clusters are designed for predefined workloads or workflows that automatically terminate upon completion of specified processing steps. This pattern optimizes costs by ensuring that computational resources are only consumed for the duration of actual processing, making it ideal for batch ETL jobs, scheduled data processing pipelines, and one-time data transformation tasks. Transient clusters support use cases like nightly data processing jobs, periodic model training workflows, and batch feature engineering pipelines where the processing requirements are well-defined and repeatable. The automatic termination eliminates the risk of forgotten running clusters that continue to incur costs. Long-running clusters provide persistent infrastructure for interactive data analysis, ad hoc queries, and experimental workloads where the processing requirements are not fully known in advance. This pattern supports exploratory data analysis, interactive notebook environments, and development workflows where data scientists need flexible access to computational resources. Long-running clusters enable use cases like interactive Spark sessions for data exploration, persistent Jupyter Notebook environments for collaborative development, and always available analytics infrastructure for business intelligence applications. There's a nice graph to show some of this. Carpenter, you're going to be using that if you're in there, these clusters. Okay. EMR storage. All right. So there's HDFS fundamentals, right? This provides a distributed fault-tolerant storage system that automatically partitions large files into blocks. The default is about 128 megabytes and distributes them across cluster nodes with configurable replication factors. This architecture ensures data durability and enables parallel processing by allowing multiple nodes to work on different portions of the same data set simultaneously. The distributed nature of HDFS provides significant performance advantages for big data processing by enabling data locality optimizations where processing tasks are scheduled to run on nodes that already contain the required data, minimizing network overhead and maximizing processing efficiency. Ephemeral nature. So ephemeral nature means that HDFS data exists only for the lifetime of the cluster, requiring careful planning for data persistence beyond cluster termination. While HDFS provides excellent performance for intermediate processing results and temporary data storage, it requires integration with persistent storage solutions for long-term data retention. This characteristic makes HDFS ideal for storing intermediate results during complex multi-stage processing pipelines, caching frequently accessed datasets for iterative algorithms, and maintaining working datasets during exploratory analysis sessions. Then you have EMR FS. Okay, so this is the EMR file system. All right, so this provides a bridge between EMR clusters and Amazon S3, and it allows S3 buckets to be accessed using standard Hadoop file system APIs. This integration enables EMR applications to read input data directly from S3 and write output results back to S3 without requiring explicit data transfer operations. The S3 integration offers compelling advantages, including persistent data storage beyond cluster lifetime, virtually unlimited storage capacity, and cost-effective storage pricing compared to maintaining large HDFS clusters. This combination enables architectures where compute and storage can be scaled independently based on the specific workload requirements. Consistent view capabilities address S3's eventual consistency model by maintaining metadata in DynamoDB to track object consistency, ensuring that EMR applications can reliably access recently written objects without encountering consistency-related errors that could impact data processing reliability. So there's three different types. HDFS, the Hadoop distributed file system, which is fast but ephemeral. There's the EMR FS, which is a S3 as a file system. It's persistent and decently performant. Then you have EBS, that's the elastic block store, which is optional for HDFS backing. Next, we'll go to EMR Serverless. All right, this is simplified cluster-free data processing. So what is EMR Serverless? This is a serverless service that eliminates the complexity of cluster capacity and its planning by automatically determining and provisioning the computational resources required for specific workloads. This approach addresses one of the most challenging aspects of traditional EMR usage, accurately predicting the cluster size needed for optimal performance without over-provisioning resources. So the serverless model particularly benefits organizations with variable or unpredictable data processing workloads. The development and testing environments where exact resource requirements are unknown, and scenarios where the cost of over-provisioning exceeds the benefits of guaranteed performance. So the automatic resource management analyzes submitted jobs to determine optimal resource allocation, and it automatically scales compute and memory resources based on actual processing requirements rather than pre-configured cluster specifications. So this intelligence helps prevent common issues such as out-of-memory errors due to insufficient resources or wasted capacity from over-provisioning. Okay. All right, usage patterns. Okay, so there's pre-initialized capacity. And this enables optimization of cold start performance by specifying baseline resource allocations that EMR Serverless maintains ready for immediate use. So this capability bridges the gap between fully automatic resource management and performance predictability for time-sensitive workloads. Organizations can specify initial driver and executor configurations to ensure adequate resources are immediately available when jobs are submitted, while still benefiting from automatic scaling for workloads that exceed the pre-initialized baseline. This approach proves particularly valuable for production workloads with known minimum resource requirements. Resource limits provide cost-effective or cross-protection by setting maximum CPU and memory consumption levels, preventing runaway jobs from consuming unlimited resources and generating unexpected changes and charges. These safeguards are essential for production environments where cost predictability is important. Okay. You can see some of this listed within. Remember to bookmark that. So what's the application lifecycle management? One, you have the job submission process. This involves creating EMR serverless applications and configuring execution roles with appropriate permissions and submitting jobs through the AWS CLI or SDK. While the underlying infrastructure is serverless, users can maintain control over application configuration job parameters. Then you have cost management, all right? So this requires explicit application lifecycle management, as EMR serverless applications continue to incur charges even when idle, all right? Whew, that's crazy. Organizations must implement proper cleanup procedures and monitoring to ensure that unused applications are terminated to avoid unexpected costs. This requirement emphasizes that serverless in the EMR context refers to infrastructure management rather than cost management, and users remain responsible for controlling application lifecycle and associated expenses. A serverless version of EMR will do certain things. It'll remove the need to manage EC2s. It'll automatically provision resources based on your Spark, Hive, Presto job needs, and it'll work on demand and scale dynamically. All right. So the key integrations with this would be S3, IAM, KMS, CloudWatch, Glue, and VPC. Why? S3 is for input-output storage. IAM is for job execution roles and permissions. KMS is for encryption of data at rest. CloudWatch is for monitoring, logging, and alerting. And Glue is for Metastore or Spark Hive metadata. And VPC is for network isolation. Okay. So some of the EMR architecture. All right. So this is a broad overview, and you can find some specific. Well, first we'll go with Spark Core. This provides the foundational framework for distributed data processing, implementing the resilient distributed dataset, RDD, this abstraction that enables fault-tolerant distributed computing. While RDDs remain available for low-level operation, most modern Spark applications typically use higher-level APIs that provide better performance and usability. Spark SQL. This introduces the data frame and dataset APIs that enable SQL-like operations on structured and semi-structured data, providing query optimization through the Catalyst optimizer and columnar storage support through formats like Parquet or Parquet. This component makes Spark accessible to users familiar with SQL while providing the performance benefits of distributed computing. The data frame API abstracts away many of the complexities of distributed computing, allowing data scientists to work with familiar tabular data structures while automatically benefiting from Spark's optimization and parallel execution capabilities. Then you have Spark ML-lib. So this provides distributed implementations of machine learning algorithms specifically designed to operate across cluster environments. Unlike traditional single machine machine learning libraries, ML-lib algorithms are architected to handle datasets that exceed single machine memory capacity while providing fault tolerance and automatic parallelization. So MLib includes classification algorithms like logistic regression, decision trees, and random forests. It also has regression algorithms, clustering implementations like k-means, recommendation engines like collaborative filtering, and dimensionality reduction techniques like PCA or SVD, all optimized for distributed execution. Then you have Spark streaming. Now, this enables real-time data processing by treating incoming data streams as a sequence of micro batches that can be processed using the same APIs and algorithms developed for batch processing. This unification allows organizations to apply consistent processing logic across both batch and streaming scenarios. The integration with AWS services includes native support for consuming data from Amazon Kinesis streams, enabling real-time analytics and feature engineering pipelines that can immediately process streaming data for machine learning applications. Okay, so pricing, always important. First, you have memory management. In Spark, this requires understanding the execution model where data is cached in memory across operations to minimize disk input output and network traffic. Proper configuration of memory allocation between execution and storage can dramatically impact performance for iterative algorithms common in machine learning. Then you have data serialization. These choices affect both performance and memory usage. With Kiro serialization typically providing better performance than Java serialization for complex data types, these optimizations become particularly important when processing large data sets or when working with complex nested data structures. Then you have cluster sizing. Now, this involves the balancing of the number of executor cores, executor memory, and total number of executors to optimize for specific workload characteristics. Machine learning workloads often benefit from configurations that maximize memory per executor to support algorithms that require holding large data sets or model parameters in memory. Okay. Instance types and spot instances. Okay. So you have a couple of different types. So you have the task node optimization, which leverages spot instances for task nodes to achieve significant cost savings, as these nodes can safely and can be safely interrupted without impacting data persistence. This strategy can reduce processing costs by 50 to 80% for workloads that can tolerate some variability in completion times. Then you have core node considerations, which require careful balance between cost and reliability, as core nodes store data in HDFS and cannot be safely replaced with spot instances in most scenarios. However, proper planning of data persistence strategies can enable more aggressive cost optimization approaches. Then you have master node sizing, which should be optimized for cluster management overhead rather than processing capacity, as the master node primarily coordinates work rather than executing intensive computations. Right-sizing the master nodes can provide modest but consistent cost savings. Then you have cluster lifecycle management. Okay. So with this, you have a couple of different things. Transient cluster strategies. These can maximize cost efficiency by terminating clusters immediately upon job completion, eliminating charges for idle capacity. This approach requires careful job orchestration to ensure that all the necessary outputs are persisted before cluster termination. And you have auto-scaling configuration, which enables the dynamic adjustment of cluster capacity based on workload demands, automatically adding task nodes during peak processing periods and releasing them when demand decreases. This capability helps optimize costs for variable workloads without manual intervention. Remember, these are charged based on the vCPU and memory seconds, and they set max capacity to prevent runaway builds. And serverless does not auto-delete applications, so please be vigilant. Okay, so we're going to go into the console. All right. Okay, so let's see. Let's go to EMR. All right. All right, we're going to EMR. So the prerequisites for this would be an AWS account with billing. You have an IAM root or IAM user. You could have a Jupyter notebook, and then you need a nice TSV file. We're just going to go, what do you call it? We're going to walk through, what do you call it? So let's create cluster. Oops, create cluster. All right, we'll name this EMR test. All right, so we can do, let's see, server. Do I see it? It was on EMR. Oh, there it is, studios. Okay, so we can create the studio. So we can have different types. We can do interactive, we can do batch jobs, we can do custom. All right, so we'll do is there a quick setup? Well, this is the quick setup pretty much. All right, so what you can do is you can do the interactive. You can go in here and edit, change the name, have a new bucket for this, and then remember that bucket, copy that to your notepad. Encrypt the workspaces with your own key. Okay, you're gonna have to get that key. All right. Create a service role or choose an existing one. We'll create one likely. We're not actually going to. And then your workspace settings, you can edit this. Application settings, remember this, the runtime role, we can do that. We're choosing existing runtime role. All right. And then you click this. All right. I don't want to, because with these costs are adding up. Okay. But the next portion would be to upload a notebook into your data. In the S3 bucket created by the studio, you put that there. And then you paste that into the notebook as the input path. And then from there, you'll be able to load with the Spark data frame, drop any null values with some filters. And basically, the Spark job would be able to look up and query like you need. And then you could do query terms like locations, names, anything you can think of. And then you can rank this by it. And then you would basically have a simple search engine for anything in your file. All right. Then when you're done, remember to, in your studios, if you have this, you click on the little icon over here, delete, stop any of the clusters or serverless or serverful apps, delete them, delete any of the workspaces, delete the studios, delete the S3 and the IAM. IAM and S3 are a little more optional. You really only get charged for usage for our S3 as far as storage or egress. All right. But that's just a basic overview of EMR. Next time, we'll go into a little more feature engineering. Anyways, if you don't mind, press the like button, subscribe, or share this with anyone you know taking the AWS Machine Learning Associate exam. Thank you, and have a good day.